Good afternoon, morning, or evening. Okay, physics last day of Unit 3 content. Of course, we still have to do our second hand in the unit, which will deal with gravitational forces and also with magnetic fields. And what we're going to do basically after that is maybe the review or outline for the quiz, and that would be it for the unit. And the last unit is modern physics, which is a pretty short unit. And mostly theory, not too much calculation, as a lot of calculation type stuff for the last unit is a little bit complex for us in high school yet. Okay, so let's finish off what we're going to do today on day 16 and the final content day in Unit 3. What we're going to look at is we're just going to look at a couple examples of that equation that we never did yet. So we're going to look at some examples of using the force field, or I guess we should say magnetic field, current equation. And then we'll look at a couple examples of just review a little bit on the right-hand rule with that force equation using your palm and your thumb and your fingers. So we'll just review an example or two of the right-hand rule. Okay, and then I'm going to post up the second hand in as well and give you tomorrow to work on it, but you might be able to get started on it today, as this shouldn't be a extremely long topic because we are almost done all the content here. So let me just turn my preview on so I can watch our time there. Okay, so the first thing is just to remind ourselves the equation that we had, okay, for force. Let's actually use the marker here. Okay, if you have a current carrying wire and a magnetic field, okay, it will produce a force on that wire or push that wire with a force. And that equation that we had was F equals the current times the magnetic field times the length of the wire, okay, times the sine of the angle between, okay, we'll just put brackets around that one, sine of the angle between the field and the magnetic field and what was it? The current flow. Okay, current flow in the magnetic field. Okay, so just to remind ourselves, force on the wire, okay, current in wire, okay, magnetic field strength, okay, length of wire. Okay, and of course theta, angle between the magnetic field and the current. Okay, and remember that if it's at 90 degrees, because we'll have some 90-degree situations as well, if you get them perfectly lined up. Okay, so let's do a couple examples using this formula here. Okay, so let's make some space here. Okay, so here's an example of something that we can use. Okay, say a 7.5 amp current is flowing through a wire in a magnetic field at 90 degrees with a strength of 0.35 Tesla. Okay, remember the magnetic field is measured in Tesla and current is measured in amperes or amps for short. If the wire has a force on it of 0.63 newtons, what is the length of wire which is in the magnetic field? Okay, so we're solving for L in this case. Okay, so I'll give you a few seconds to write that one down if you're taking your own notes as you go. And basically, we're just going to apply this. Now, in this particular equation, we have really 5 different variables that we have to take into account. We have the force, we have the current, we have the magnetic field, the length of the wire, plus we have the angle that could be between the two, the magnetic field and the current flow. Now, we generally, you get the best result when you have it at 90 degrees, gives you the most force, right? Because sine of 90 is 1, so you want it at 90 degrees exactly, gives you the most potential force that you can use. Okay, so let's attempt solving this. So the first thing I like to do is write down what we know here. We know that the current, which is capital I in our formula, is 7.5 amperes. We know that the magnetic field, which is B in our formula, is 0.35 Teslas. Okay, these are all derived units. So they're not in their base form. So canceling and things like that, we might have to break them down into there, or we might just have to remember what they mean. And we know that the force is in newtons. Whoops, let's put the actual result there. 0.63 newtons. Okay, and the angle is at 90 degrees, so that's going to give us the maximum. Okay, so that's going to tell us that we have to do a sine 90, which we know is 1. Okay, if you check it on your calculator. Okay, and what we're trying to find here is what is the length of wire that is in the field in terms of meters. Okay, now the length of wire is going to come out in meters. Everything else is a derived unit named after some scientist. So amperes, for example, are coulombs per second, okay, and those kinds of things. So one of the harder things to do then is to kind of check with units and do our canceling, but it's also easier just to remember what each unit is. So if you have something in milliamps, make sure that you change it to amps. If you have something in like centiteslas or something, make sure it goes to teslas. If you have kilonewtons, make sure it's in newtons. Okay, and the length will always come out in meters. So if they give you like centimeters or something, change it to meters. So remember that part. So let's apply the formula. Okay, the formula that they give us is, or that we have, is force equals I B L sine theta. Okay, so if we want to isolate the length by itself, we simply have to divide IB sine theta out on the right side and the left side. So if we want to F over IB sine theta to come out, and that's going to give us L. Okay, if we rearrange it a little bit. So then we can plug our numbers in and calculate what we would have for our results. Okay, so the length of wire would be equal to force 0.63 newtons over the current of 7.5 amps times the magnetic field of 0.35 Teslas times the sine of 90, which is 1. Okay, so if we work that out a little bit, do a little bit of working here, we get 0.63 over, and sine 90 is 1, so we can just multiply that by 1, so it's 7.5 times 0.35 times sine 90, or 1, equals 2.625. Okay, and then if we do a division there, 0.63 divided by 2.625, you get 0.24 meters. Okay, two significant figures seems about right for that one. So that would be the length of wire in there. Okay, so that's solving for one of the L or the 4 in that equation given everything else. Okay, so in this case, yes, as we can see, right, it's going to be in meters, okay, and two significant figures because there's 2 there and 2 there and 2 there. So two significant figures, 0.24 meters. Okay, let's do one more example. Here, for a calculation, let's calculate a magnetic field, maybe. We'll do one like that. Okay, let's do it on the second page here. Okay, I'll just copy it again here from my bank of questions. I don't have that many, but I have a couple over here. Okay, so this one has some milliamps in it, okay, and some centimeters, so I have to be careful with the units. So it says a current carrying wire has 18 centimeters of length in a magnetic field. The current through the wire is 650 milliamps, and the force experienced by the wire is measured to be 0.68 newtons. Find the magnetic field strength given, and so this should be given here, not give, given a 90-degree orientation between the current and magnetic field, period, which is traditionally what we have. Okay, so I'll give you a second to write that down if you're taking your own notes, and then keep in mind that we have to convert this to meters and this to amperes, okay, and then the newtons is in the correct unit there, and then we'll get the correct unit, so we get Tesla for the magnetic field. Okay. Okay, so if we were to write out what we know, okay, and then convert them to the appropriate units, let's do current first. Okay, current is equal to 650 milliamps. Okay, we know that there's 1,000 millimeters in a meter, same thing, there's 1,000 milliamps in an amp. So we have to divide by 1,000 to get how many amps there are. So this is 0.650 amps. Two significant figures, maybe 3, I don't know. This could be a significant 0, but if it's not marked, probably isn't. This is only 2 significant figures, so probably everything's going to turn out to be 2 significant figures. So that's our amperes. Okay, then we can do the length of the wire, 18 centimeters. Now we know that there's 100 centimeters in a meter. We want to go to meters, so we got to divide by 100, 0.18 meters. Okay, that's in the appropriate units. Okay, we know that the force is already in the appropriate units, so we could just write that one down. .68 newtons. And we know that the angle is given at 90 degrees. So we know that sine 90 degrees is going to give us a 1 when we do sine 90. And what they're trying to get us to figure out here is the magnetic field strength in Teslas. So B is what we're trying to solve for. Okay, again, we can rearrange the formula or we can plug it in. Okay, last time we just rearranged it. This time let's just plug it in and then work it out algebraically in case you're more used to doing that. Okay, so that would be the force equals the current times magnetic field times the length of the wire times sine theta. Okay, so if you want, I like to rearrange it first, but in this case, we're going to do it the other way. In case you do it that way, let's put in the force, 0.68 newtons. The current, 0.65 amperes. B is blank. L is 18 centimeters or 0.18 meters. And sine 90. Okay, so what we want to do is we want to leave this one and multiply these three together to get a number beside the magnetic field variable. So this is still 0.68. And then if we multiply with our calculator, sine 90 is 1. So 1 times 0.8 or 0.18 times 0.65. Okay, if you do those, you get 0.117 B. Okay, now we know because we use the appropriate units here that the magnetic field is going to come out in Teslas. Okay, we could break them into all the base units and start canceling, but that would be quite a challenge as they're all derived units. So it might take us a bit. So we just remember that if we have these in meters, amperes, and newtons, we'll get an answer in Tesla. So we take 0.68 and we divide 0.117. We get 5.81, or if we do two significant figures, 5.8 Tesla. Not even sure how strong a Tesla is. That's stronger than the last one we had. And that's our couple examples that we did there, okay, similar to that. So that's using that equation. Okay, that's taken us through, 18, 19 minutes there. One other thing that I wanted to look, if we look back what we had at the beginning, is I wanted to look at just kind of review the right-hand rule. On one of the assignments, I have a drawing there for you to use the right-hand rule. And I didn't do a really similar one yet for an example. So I'm going to do one of those examples here, just so you don't get confused on the hand in. It's going to come up. So, and that'll be our last thing for today. And then you can get started early on that hand in if you like. For today, it's a shorter hand in, like maybe 9 questions. And you can work on that. And then next day, I'll go through the outline for the quiz, schedule that in a week or so, and then we're into the last unit, modern physics. Okay, so let's do an example here. This one I'm going to draw out. So this is just a review of the right-hand rule. Use the right-hand rule to find the current in the wire. Okay, we'll do a couple of these drawings, okay? Okay, so I'm going to draw this one out here on screen. Let me just bring it up on my my drawing bank here, or my question bank on the other side here. I've got a couple of them that we can look at here. We'll pick a couple of these to do here. Give it a sec. Takes a while for the thing to pop in. Where are you? There you are. Okay, so let's say that we had a magnetic field coming out of the page. So let's draw a bunch of dots here. We'll use black, yes. Skinny one. Okay, so let's actually, I'm not going to put it's not in the wire, so I'm just going to put dots. That's how I'll draw it on there, because it's not a current carrying wire, it's just the magnetic field. So let's say that we had a field, magnetic field. So I'm going to draw a few rows here of this magnetic field. Okay. So this is the magnetic field and it's coming out of the page. Okay, we're not going to worry about the size, we're just going to worry about the direction that it's in. Okay, so we have that. And let's say that we have a wire sitting in it. Just hang on a second here. There we go. I'm just going to pause here. I got a quick email. Then I'll get back to this. Sorry about that. Okay, so, and then let's draw a wire. I'm going to draw it in green here. Let's say the wire is perpendicular here, perfectly. Okay, so this is a current carrying wire. Okay, across the field, and these are at 90 degrees between those two. That one's coming out. This one's going to be going either left or right. We don't know. And let's say that it's experiencing a magnetic force going up. Okay, so let's put the magnetic force with some arrows here. Oops. Let's use a dotted arrow and let's make it, I don't know, purple. Okay, so this represents the force on the wire. So we'll write that in purple here. Okay, so it says use the right hand rule. So okay, remember the right hand rule. Okay, if we go on the wire, point our fingers point in the direction of the magnetic field, and our palm points in the direction of the force, and our thumb points in the direction of the current. So if we put our right hand like this with our palm upwards, okay, palm upwards, it's fingers coming out of the page, palm is pointing up, and it's not down like this, pointing towards us, but it's pointing toward out of the page. Palm is up for the force. That means our thumb is pointing this way. So according to this, the current should be flowing to the left on the screen. So the current direction, which we'll put would be left. by the right-hand rule. And there we are. Pretty easy to do that one. Okay, and that I just wanted to do one like that because I don't know if I've used the magnetic field. Okay, the one on the hand is similar to this. There's a wire, and then there's a magnetic field and a force. Might be going up, down, across, and they're all 90 degrees to each other. Okay, just remember that dots mean coming out of the page, X's mean going into the page if we're talking three dimensionals. Okay. Okay, let's do one more right-hand rule one here. Okay. Use the right-hand rule. To find the direction of the magnetic field. So let's say that we have, this time, let's say we have a coil. So let's say that I have something like this. Let's just draw it. Let's just draw a coil like this that we had before. Okay, let's draw about 4 of these. Okay, so let's say that it's going in on the bottom. So it's flow. Let's have it go. I can't remember which way I did it before, but let's say it's going in on the bottom. So X is on the bottom. And that's the current flow. Coming out on top of these loops. So that means the right-hand rule for a solenoid is you curl your fingers in the direction of the current. So it's coming out on top, so your fingers have to be laying over the top. So you got to grab it by the bottom and curl your fingers up and around to the top. So that means that our thumb is pointing to the right. Okay, so our thumb points right. So that means the North Pole is on the right side of the coil. Okay, and then we'll draw the magnetic field in here. Let me change colors here, and give me a second again. I got one more email here. Okay, sorry about that. So changing colors here. Okay, magnetic field. Oh, that's not changing colors, is it? There we go. Going around like this. Okay. Going in on the south, out on the north. Oops. That one backwards there. There we go. Out on the north. Not in on it. Okay, so this is our magnetic field. Okay, so that's our stopping point. The unit content is now over. So We do have one more handed. I'm just going to pop it over here for you, just kind of see it. So you can start that today. I will give tomorrow's period to work fully on it. Okay, so let's just open it up here for a second. Give me a second here. Where are you? There you are. Fields unit. Okay, and this one is in PDF form. I believe yes. So hopefully there's enough space on it. Okay, so if you look at it, we'll just slide her over here. Okay, hand in number 2, gravitational magnetic fields. I was going to split it into 3, but 2 works out good. Okay, the first one there, okay, that's talking about Newton's law of universal gravitation. Okay, here's an explain question. Okay, you got to think ratios because it's not giving you numbers, so it's a little bit of thinking. It's universal gravitation. Didn't leave a lot of space there, sorry. Okay, then in here we've got one of the questions where you have to use gravitational field. Okay, be careful with units here. Okay, it has to be in meters. Okay, not kilometers. Okay, over here we've got one, again, that's dealing with orbital period. Okay. Okay, here's an explain why, just talking about Einstein's gravitational field. Okay, and then here is the the magnetic field stuff around a coil. Okay, current carrying wire. Okay, 90 degrees relationship. Okay, that's one of the formula we just used. Here's another right-hand rule, and here's another right-hand rule. Shouldn't take you too long to do this. Okay, and that's a hand in, and that's unit 3. Okay, tomorrow I'll put up, you could be able to work on this, a work period. Day after that, I'll put up the outline for the quiz. Okay, so that's where we're going to stop today. You can start on your hand in if you want, and we'll see you tomorrow.